last meeting, we answered problem number 1 for moment of inertia. So now let's continue on to problem number 2. So number 2, determine the moment of inertia with respect to the x-axis for the circular area shown in the figure. Okay, so once again, we've already answered 1. Moving on to number 2. Okay. So for number 2, we want to know moment of inertia about the x-axis. Therefore, we're looking for I sub x. Okay? And the equation for I sub x is integral of y squared dA. Now, usually, when we're looking for moment of inertia about the x-axis, our dA would be a horizontal element. That's why here we have this horizontal element. So that's your differential area. Now let's rewrite our equation. Integral of y squared is still y squared. Then let's get an equation for our differential area. So once again, our differential area is a rectangle, so that's just base times height. Now the question is, what is our base? What is the value of this? Correct, say it's 2x. So why is it 2x? So considering first at the center, right? Your centroid is at your axis is at the centroid, and then we have two lines of symmetry, meaning the left and right is equal to top and bottom. So considering this point, the length or the base of your area from the y-axis to the edge is your value x, right? So even though this is your area, okay, from this point to this point, that's still x. Because all of the points on this line is represented by the variable x, okay? So that's just half your area. We still have another one here. And again, this is symmetrical, it's a circle. So for whatever value you have on the right side, it's the same for the left side. Therefore, total base is 2x. Okay, so that's why base is 2x. And then height, that's your differential height, y, so dy. And then get the range of your element. So the lowest range of this is at this point, and the highest range is here. So at this point, the bottom of your circle, and then your reference is from this point, which is again at the center. So basically, that's from center to edge, and that's equal to radius of your circle. So at this point, this is negative r, since again, it's below your axis. And then here at the top, that's just positive r. Therefore, the range of your element is moving here to the lowest point up to here to the highest point. So it's negative r to r. Okay, next. Our variables should be in dy, right? This is where we'll base our variables on. I have an x here, so I need to rewrite x in terms of y. And to do that, again, recall this is just a circle. And we know the equation of a circle. It's x squared plus y squared equals r squared. Therefore, x is just square root of r squared minus y squared. So let's sub that here. So this becomes integral of y squared times 2, and then x is just this, so sub that in, integral of r squared minus y squared, and then dy. Okay, now solving for this integral is kind of complicated. Okay, so I'm not going to show you that anymore, since that is not what we're concerned with. We're not focusing on integral calculus. I'm just showing you the process by which the equation for the moment of inertia of a circle is made. So just know, this is your process, and then using your integral calculus, you can create an equation for I sub x. So I'm not going to show the process, so using differential equation. Just know that after solving, you should get I sub x, And since our axis is about the centroid, so this is centroidal moment of inertia. And that's pi r raised to 4 over 4. There. So that's our answer for number 2. Any questions so far? Please answer in the chat. Okay, great. Let's move on to number 3. So number 3, a rectangle is 3 inches by 6 inches. Determine the polar moment of inertia and the radius of gyration with respect to a polar axis through one corner. So we're looking for polar moment of inertia, so that's J. And then we're also looking for radius of gyration, so that's K, about your polar O. So that's K sub O or K sub J. So let's begin. So first, let's take the polar moment of inertia. Recall, that's just I sub x plus I sub y. Okay? And then, for I sub x, that's moment of inertia about the reference x-axis. This is your reference x-axis. And if you remember, we already have an equation for the moment of inertia of a rectangle. This is just a rectangle about its base. So let's look at it again. So at letter B, this is moment of inertia of a rectangle about its base. The equation is bh cubed over 3. So we can just use that instead of deriving the equation. Okay, so ix, again, bh cubed over 3. Now what about iy? How do we do that? Now again, like what we did in the previous example, if you've noticed, there's a pattern here. So let's look at centroidal moment of inertia. Centroidal moment of inertia is bh cubed over 12 about the x-axis. And then about the y-axis, okay, here, it's hb cubed over 12. So the reason for that is because along the y-axis, on its edge, what happens is you can also analyze it as moment of inertia about the base if you rotate your rectangle. So to illustrate, okay, again, moment of inertia about the y-axis. Let's redraw that. This is now your y. This is your x, right? This is your h. This is b, correct? And using these variables, we already know moment of inertia of this shape about this axis. That's base, right, which is denoted by h, times height cube, which has the variable b, and then over 3. Okay, so this is the moment of inertia about the y-axis. So again, we did that by just rotating our figure. So let's write that. hb cubed over 12. Now let's just direct sub. Okay, so base is 6 times 3 cubed over 3. Oh, sorry, this is 3. Think about the base. And then plus height is 3 inches. And then base is 6 cubed over 3. Please solve. What's the answer? Correct. Pauline and Naomi. Pere Nyoso. It's 270. What's the unit? Correct, Colin and Rafaela. So Pangalangan and Pere. Inch to the 4th. Why? Because base is in inches, height is inches. So inch times inch cube, that's inch raised to 4. Okay, so that's the first part. Next, we're looking for radius of gyration about pole. So that's K sub O or K sub J. And then if you recall the equation for that, that's just integral of J sub O over cross-sectional area. So J sub O, that's 270. And then not cross-sectional area. Area of your shape is a rectangle, so that's just base times height. So 6 times 3. Please solve. What's the answer? Correct. Correct, Pamela and Zaira, or Piz. Okay. So 3.87. What's the unit? Correct, Rafaela and Naomi. Pangalangan? Yes. Inches. Why? This is raised to 4. Area is squared. So you'll get square root of inch squared. And that's just inches. Okay. And that's our answer. Any questions for number 3? Please answer in the chat. Okay, great. Let's move on to the next item. Number 4. Determine the moment of inertia and radius of gyration with respect to a polar centroidal axis of the cross section of a hollow tube whose outside diameter is 6 inches and inside diameter is 4 inches. So again, we're just looking for moment of inertia with respect to a centroidal axis or polar centroidal axis meaning we're looking for polar moment of inertia. And then radius of gyration, again, with respect to a polar centroidal axis, so that's K sub O, same with the previous question. Let's begin. So we're looking for J sub O, right? So that's Ix plus Iy. Now there's a problem here. The equation that we know so far is that of a circle. This is a ring, okay? So what we're gonna do here is kind of similar to what we did with centroids, which is we're taking the area as a separate entity, and then when we use it in our equation, it just has a negative sign. So same thing here. We can take this as a whole, so as a circle, since that is what we know. Take the moment of inertia of this total circle and then subtract it by the moment of inertia of this empty space. So again, it's just a whole subtracted by the empty space. That's what we'll do. So before I write it in the equation, I'm gonna separate your moment of inertia so that we'll see it clearer. So Ix. Now, since this is a circle, do you think moment of inertia about the x-axis is the same as the moment of inertia about the y-axis for a circle or ring? Yes or no? Answer in the chat. Is Ix the same as Iy for a circle or ring? Okay, everybody, please answer. Mm-hmm. Okay, very good. Most of you got it correct. The answer is yes. Why? Because this is your x-axis, right? Sorry, this is your x-axis. We're gonna take moment of inertia about that. We did that earlier in this problem. Now to take moment of inertia about y, you can just rotate that. It'll become this way. So y, x, and then your circle. And you'll notice that the dimensions are still the same. This would still be your dx. This would become dx. This would become y. So your base now is 2y, so on and so forth. And the equation, and you'll see that these two are almost the same, or like actually the same figure. So that means Ix equals Iy. Okay? Again, to put it simply, if you have two lines of symmetry along the centroid of a figure, Ix would equal Iy. For example, another thing that has two lines of symmetry is a square, right? we have a line of symmetry here, meaning Ix and Iy for this square is the same. Okay, so let's continue. And the equation for a circle is pi r raised to 4 over 4. Okay, so pi r raised to 4 over 4. So let's sub pi r. So radius of your total circle or your outer circle is 3. So 3 raised to 4 over 4. Please answer in terms of pi. Mhm. Again, in terms of pi. So correct. Uh, okay. 32. Correct, Nicolas. And Rain. Simon. So, Pochero Bueno. It's 81 pi over 4, or you can also write it as 20.25 pi. Again, I like writing it in terms of pi because I don't have to store it in my calculator. So now we have the moment of inertia of our area, total area. Next, let's get the moment of inertia about our empty space. So let's call that E or I, up to you. This is just a variable. So I'll call it E for empty space. So similar to your solid area or full area, moment of inertia of the empty space is still a circle. The shape of your empty space is still a circle. Therefore, centroidal moment of inertia about the x and y axis are the same. So I, y, so that is I. So R here is outer radius. And then let's call or like capital R. And then here the radius of our empty space is small r raised to 4 over 4. And then let's sub that value. That's 2. Please solve. What's the answer? Correct. 4 pi. Correct, Lauren. And Simon. Chua. Chero. Chua. Okay. It's 4 pi. Simply 4 pi. Okay. Now to solve, we can do it or organize our answers in two ways. So that is taking the polar moment of inertia for the x-axis first. So again, that's Ix plus Iy. So this axis is actually about the center, so you can write it as centroidal moment of inertia. And then let's isolate the answer for your x. So this is Ix minus the empty space. So minus I x sub e plus I y minus y sub e. So as you can see, we're subtracting the empty space. Or another thing you can do is take the polar moment of inertia of your solid or full area and then subtract by the empty area. So that would be Ix plus Iy minus Ix sub e minus Iy. Plus and minus. Okay? So up to you, whichever is easier to understand for you. Again, you can just take it by axis or take it by shape. I'm gonna do by axis. So let's sub in our values. Ix is just 81 pi over 4 minus IXC, that's 4 pi. And then since they're symmetrical, you can just multiply by 2, or you can just write it out as well. IY is the same, 81 pi over 4 minus IY sub A. Please solve. What's the answer? Now, if we're getting the final answer, you should write it in decimal format, not in terms of pi. Okay. Again, final answers should be in decimal. So correct, Alyssa and Colin. Very my what else? Nicholas correct. Bueno. Okay. So 102.10. And then our unit again is inch raised to 4. Okay, and then we're gonna use that. So store it in your calculator. Because we need your K sub O as well. So that's radius of gyration about your polar axis, K sub O. And again, the equation for that is just J sub O over area. Okay, so we already have J sub O, so use the stored value of that. So that's 102.10. I'll just write its variable. And then cross-sectional area is the area of your ring. Okay, it's not the total area of your circle. So area of your ring is just pi r, pi times radius of the outer ring squared minus radius of the inner ring squared. So recall your geometry. Pi, outer ring is 3 squared, inner diameter, inner radius is 2 squared. Okay, please solve. What's the final answer? Correct, Naomi and Zaira. Yes. Points for me. Both. Correct, Lauren. Jayla. It's 2.55. Okay. Once again, unit is just inches. Inches. Okay. So that is number 4. Any questions for number 4? Please answer in the chat. Okay, since we don't have questions, let's move on to number 5. So number 5 is a bit different. Determine the moment of inertia for the shaded area shown in the figure about the x-axis. We're looking for I sub x. Okay. Now, unfortunately, unlike the previous examples, we don't have an equation for whatever that is, which is actually the area of a spindle. So since you don't know, we're going to have to use the integration formula, which is integral of y squared dA. Okay, so whenever you have an irregular shape or you don't know the equation for the moment of inertia of that shape, you can still use this. And then this is moment of inertia about the x-axis. So usually we're gonna use a horizontal strip. That's why we have this here. Okay, so let's rewrite our equation. Y squared, differential area. So let's rewrite the area of that. Again, that's a rectangle, so base times height. So let's get the base. So this length is your base. It's not just 100, it changes. So for example here, okay, for this part, the distance from the y-axis to this point is just your x, right? For all the points along this line, it's just x distance away from your y-axis. That's how your equation works. So therefore, if we're just looking for the length of this, it's this total value, 100, minus x. So even, let's say, our bar is here. So again, this total length is 100, and then we need to subtract by this length, and that length again is just x. Since all points on your graph is x distance away from your y-axis. Okay, so this is still y squared, and then 100 minus x, then height dy. Then let's get its range, upper and lower limit. So its lowest limit is here, so that's 0, right? And then the highest limit is here, okay, which has a height of 200 millimeter. So this is 0 to 200. Okay. Now we have another x variable here, when we need all of our variables to be y. Again, the basis of our variables would be this differential. So luckily, we have an equation already relating y to x. So y squared equals 400x. Therefore, x in terms of y is just y squared over 400. So let's rewrite this again. Y squared integral of y squared times 100 minus y squared over 400 times dy from 0 to 200. Now again, our subject is not integral calculus, it's mechanics. So that means we can just use our calculator to solve for the value of this. So please solve. What's the answer? Correct, Marilyn? Again, you can just use your calculator. And who else? Correct, Francisco. Yes. So it's 10666, etc. A lot of sixes. Or you can just use or write it in scientific notation, which is 107. Okay, let me get the actual answer. Squared times 10666, right? Yep. So 106.67 times 10 raised to 6. Then unit, they're all in millimeters. So millimeter raised to 4. That's an answer. Okay. Since you have a calculator, it's easy to take the integral. But if you want to try, you can also do this manually. Now that is using a horizontal strip. So does that mean that whenever we have moment about x-axis, you always have to use horizontal strip? The answer is no. If you want to, you can use a vertical strip as well. So let's try that. Let me copy this drawing. So let's try another solution. Or okay, then we're not using that anymore. So let's try erasing that. And then we're gonna use a vertical strip. I'll show you how to solve for that. So let's say here. And okay. So equation is the same. Integral of y squared dA. Now that's uh, hard if you do it that way, y squared dA. Because your differential area again changes. So the easier method to solve for this is taking the moment of inertia of this rectangle, okay, again, rectangle alone, and then, so if you divide this into very small rectangles, right, okay, so just imagine that's full of rectangles. You take the moment of inertia of 1 bar, and then you're going to take the moment of inertia of all of these differential rectangles. If you take the summation of all of those differential rectangles, you'll eventually get the moment of inertia of your total shape. Okay? So once again, instead of doing it this way, let's just consider one rectangle, right? This is a differential rectangle. Your total shape is made up of the summation of your differential rectangles. That means total moment of inertia. Let's see. Total moment of inertia about the x-axis is the summation of your differential moment of inertia of each rectangle. So since this is differential area instead of summation, that's integral. So integral of differential moment of inertia of each rectangle. So let me just write that dix differential moment of inertia of the rectangle. Rectangle being this differential area. Okay, now how do we get that? So now just consider your rectangle. So that's moment of inertia of a rectangle about its base. Okay, now we can't use bh cubed over 3 because the height of this changes. So we'll do it in terms of variables again. Now one thing about this is we already know the moment of inertia about its center, right? So that's bh cubed over 12, where base is dx, height is, oh, sorry, yeah, never mind. So again, considering a rectangle, the moment of inertia of a rectangle about its base, which is the x-axis, is bh cubed over 3. Let's write that in terms of the variables here. So base is differential x, height is y, right? Y. Because this is always the height. So for example, if this is your element, this height is also equal to y. Because again, same as the earlier analysis, all the points here are y distance away from the x-axis. So that denotes also the height of your rectangles. So that is integral of dix, different moment of inertia of your rectangle, is bh cubed over 12. Base here is dx, height is y, and then base over 12. 3 rather, or base 3. Okay, and then take the limits. So since we have a vertical element, we have the leftmost limit and the rightmost limit. So leftmost is 0, and then rightmost is at this point, so that's 100. Okay, and then let's simplify. So once again, my differential is in terms of x. I have a variable y, so I need to change that. Integral of, so y, I'm gonna just factor out 1/3. 1/3 y cubed dx, and then let's rewrite y cubed. So let's go here. So y is equal to square root of 400x. So y cubed is square root of 400x raised to 3. Then dx. And then 0 to 100. Okay, so try to get the answer for this. What's the answer? Okay. Correct. Joaquin. Ilustre. Correct. Then correct, Marilyn. But I need the value again. And then correct, Rafael. Up. So it's still 106.67 times 10 raised to 6. And limiter raised to 4. Okay, there. Let's check, double check. We have the same answer. Okay, if you've noticed, there's a bit of a discrepancy there. Okay. So there's a discrepancy of, I think, 4 units. Now, the reason for that is because we're approximating each area into a rectangle. So if we try to zoom it there, and then these are our rectangles. The areas of these shapes are not included in the equation. Okay. However, since this is a very, very small area, what's not included in our equation is negligible. So that's why you can also do this. But the more accurate approach is what we did in our first solution. Okay, again, this is considering the entire area here. Okay, we're using the moment of inertia of the rectangles instead of taking the total area of your shape. That's why, again, these shaded regions are not considered in the solution. Okay, that's it for number 5. Any questions for number 5? Please answer in the chat. Okay, so once again, taking a horizontal or vertical element does not mean that your answers will exactly be the same. There's a small difference between them. So since you don't have any questions, let's move on to the next topic. So the next topic is moment of inertia for composite areas. So for the previous examples, we only have one shape that we're solving for. So similar again with your centroids, after solving for just single shapes, what we're focused on is solving for composite areas. So a composite area consists of a series of connected simpler parts of shapes such as rectangles, triangles, and circles, as you've noticed in the topic centroids. So provided the moment of inertia of each of these parts is known or can be determined about a common axis, then the moment of inertia for the composite area about this axis equals the algebraic sum of the moments of inertia of all of its parts. So again, for a composite area, we're just going to take the algebraic sum in the same manner you did for centroid. This means that for empty spaces, we're going to use negative. Okay, so for us to better understand, let's look at these equations. So these are the moment of inertia and radius of gyration of common shapes. So you already know the rectangle, right? About its centroid, so Ix bar, bh cube over 12, and then about its base, it's bh cube over 3. And then along the y-axis, it's just the opposite, so hb cube over 12, and so on. And then radius of gyration about the centroidal axis, or centroidal x-axis to be more specific, is h over square root of 12. And then moment of radius of gyration about the base is h over square root of 3. So the centroidal axis and the reference axis is given in the drawings to the left. Next, let's consider a triangle. So your centroidal axis is here, and then the reference x-axis is at the base. So centroidal moment of inertia of a triangle about its x-axis is bh cubed over 36, and then about its base is bh cubed over 12. Radius of gyration about its centroidal x-axis is h over square root of 18, and then about its base is h over square root of 6. And then moment of inertia of a circle about its centroidal x-axis is pi r raised to 4 over 4. That's the same as its moment of inertia about the centroidal y-axis. And then you've noticed polar moment of inertia. So let's look at our example earlier. So it's just moment of inertia, right, times 2, since they're the same. And then since we multiplied by 2, these are our equations. So multiplied by 2, 4 will cancel out. This will become pi r raised to 4 over 2. Then radius of gyration, r over 2, about the centroidal axis. Then r over square root of 2 about your pole O, or polar axis. And then for a semicircle, I sub x, which is moment of inertia about the base of your semicircle, is the same as the moment of inertia about your centroidal y-axis, which is pi r raised to 4 over 8. And then it's different from the centroidal x-axis. So moment of inertia about the centroidal x-axis is 0.11 r raised to 4. Radius of gyration, again, about the base x and about centroidal y is r over 2. Then radius of gyration about centroidal x is 0.264 r. For a quarter circle, here, moment of inertia about base x and height y is the same. Pi r raised to 4 over 16, same as its centroidal x-axis and centroidal y-axis, that's 0.055 r raised to 4. So that means radius of gyration of base x and base y is r over 2, and then for centroidal x and centroidal y, it's 0.264 r. And then lastly, you have an ellipse. Okay. About an ellipse, moment of inertia about the centroidal x-axis, or to be more specific, the major axis, is pi ab cubed over 4. And then about the minor axis is pi ba cubed over 4. And then radius of gyration about the major axis is b over 2. And then about the minor axis is a over 2. Okay, so just memorize all of these equations so you don't have to derive anymore. Okay, so let's have a few examples. Let's start with number 1. Determine the moment of inertia of the area shown in the figure about the x-axis. So this is pretty similar to the solution earlier when we have a ring. So that's total area minus empty space. So let's do the same for this. Okay. So number one. Our total shape here is R, right? Not R, rectangle. So let's take the moment of inertia of your rectangle. And about what? About the x-axis shown. So x-axis is here, the base, about the base. You know the moment of inertia of a rectangle about the base, right? It's dh cubed over 3. So I call it I sub r to denote rectangle. Then let's solve. Base is 100. Total height is 150. And then 3. Please solve. What's the answer? Correct. Colin, Joaquin, Pere, Ilustre, Simon, Pere, Tu, Ilustre, Cheo, Tu, Asagi, Rafael Kerr. Yan. Let's write it in scientific notations so that we don't write a very large number. So it's 11.25 times 10 raised to 7. Okay. And then next, take the moment of inertia of your empty spaces. So this is just a circle. I'll call that I sub c. Anybody give me the equation for moment of inertia of a circle? Got its centroidal axis. Okay, very good. So correct, Marilyn, Colin, and Buena. I'll give you all points. Opeliosis, Terry, Buena. Okay. So correct, it's pi r raised to 4 over 4. So that's for a centroidal axis. Now, too bad for us, that's not where our reference axis is. Our reference axis is here at the base. So to get moment of inertia about the base, remember we have this parallel axis theorem. So very good, Colin. That's the actual equation. So I sub c is, if you recall parallel axis theorem, it's I bar plus AD squared. So IC bar plus AD squared. You already know what IC bar is. IR raised to 4 over 4 plus A, area of the circle, that's just pi r squared. And then distance. This distance is the distance of the centroidal axis to your reference axis. So from this point to your reference. So it's given 75. So let's sub in our values. So pi, radius is given 25. Okay, make sure your units are uniform. And then plus, okay, 25 squared. Distance is 75 squared. Please solve. What's the answer here? Correct, Lauren and Lloyd. So, points na wells. Okay, correct, Lauren. It's 11.35 times 10 raised to 6. We'll store both of those in our calculator so that it's easier instead of typing this out. So to get our final answer, moment of inertia of everything about the x-axis is your moment of inertia of your shape, which is a rectangle, so IR minus IC. IR is this, IC is this. Get the difference. What's the final answer? Correct, Paolo and Lloyd. Although vessels. Okay, so it's 10.11, or we can write 101.15 times 10 raised to 6 millimeter raised to 4. Yeah. Just so we include all of the significant values. Okay, so that's our answer. So it's similar to your ring. That's number 1. Any questions for number 1? Please answer in the chat. Okay, no questions. Let's look at the rest of the problems. This is number 2. Okay. So looking at number 2, determine the moments of inertia for the cross-sectional area of the member shown in the figure about the x and y centroidal axis. So we're looking for 2 things: moment of inertia about the centroidal x-axis, moment of inertia about your centroidal y-axis. So we have this figure. Okay, we're only concerned with the cross-sectional area. So it's this. So this is an odd shape, right? But you can divide it into regular shapes, specifically rectangles. So there's only 2 problems left for the term, I believe. So number 2, 3, and 4. So in order to minimize the amount of information that you're getting before your quiz number 2, quiz number 3, I'm gonna leave the solutions for the rest of the problems for next meeting on Tuesday. I don't think there's a holiday on Tuesday, right? August 3. So I'm gonna continue the lecture with, I'm gonna continue the solution for 2, 3, 4 on Tuesday. This Saturday, you have your quiz number 3. Again, the coverage is just centroid. Okay, so moment of inertia is not included yet. And then modular exam number 3, topics are centroid and moment of inertia composite areas. Okay? Do you have any questions, concerns? Saan po? Sa Zoom. Next week, Saturday. This Saturday, 2 days from now, is your quiz number 3. Okay. Zoom meeting. It's the same as your previous exams. So Blackboard. Okay. So same thing as before, no difference. Zoom meeting, Blackboard, answer, upload solutions. Same thing with modular exam. Zoom meeting, Blackboard, upload solutions, answer. Also, next week is the deadline for your Coursera week 5, I believe. So try to answer that now. What else? Any other questions, concerns, clarifications? No more? Sure. By the way, for those who are wondering, if you got a 0 on the exam, that's because you didn't upload solution. Okay? So don't forget to upload solution. If you don't upload the solution after the hard deadline, you still get a 0 on your exam. Please be careful of that. Right? Before I dismiss you, oh, may poll ba dito? Maybe there is. So try creating a poll. Since we have a lot of time. Ma'am, sa IP exam, kung wari po, pag nakascore ng 80, 70 over 100 pa rin po ba makukuha? No, your score for the IP exam will be 80. What you're gonna look for is your grade under modular M, either M1 grade or M2 grade, and then there's a parentheses there for IP students. That's what you're gonna look at if it's already 70% or higher. 70% is the passing. So you get 70, your final grade for that module is 3. Even though you get a 1.25, let's say, on your M1 grade for IP students, your final grade is still 3 for that module. Okay? Any other questions? Oh, let's see nga. Yes, if you got an IP, you're gonna base it on the grade that had the parentheses of for IP students. So your final grade there is what you'll get. M1 grade or M2 grade without the parentheses for IP students is what's gonna be in your card or in your records. Okay, that I have to do that manually. That's not automatic. So just wait for me to update your grade. Okay, so I'm gonna check that from time to time. Again, if you passed or if you get 70 and up for the module M1 grade for IP students, then you're fine. Okay, can you see the poll? No? Okay. Can you see it now? Okay, choose. You can choose both. What are you into, K-pop or anime? Choose in the poll. Click the poll. You can. I think you can choose both, so you can choose the other one as well. Okay, hindi pa bumoboto. Boto na. So it seems like anime is in the lead. A lot of you like anime, which is nice. Okay, give me a second. Okay, winners anime. So let's talk about anime. Can anybody give me? Oh, oh no, kita yun. Let's see. Can give me either the English or Japanese title. Can anybody give me the title of this anime? Nope. What's the title? Very good, Miguel. I'll give you plus points. Who else? Anyone recognize what that anime is? Okay. Oh, it's very good, Alyssa. Okay. This might give you plus two. Might plus two. Four. Ah, yes. This is isekai, but it's a nice isekai. So I really enjoy this anime right now. Today, well, not today. This season, this has a season two. Yes, it's Hamifura, or My Next Life as a Villainess, or the shortcut of that anime is Hamifura, because its title is pretty long. So it's Otome game no Hamitsu flag Shikai Ashikanai Akuyaku Reijo ni Tensei Shiteshimatta. It's very long anime title. So it's all My Next Life as a Villainess, All Routes Lead to Doom. That's a total title of this anime. Or you can just type My Next Life as a Villainess. Or in Japanese, Hamefura. So this is very funny to me. So basically, this is the girl that got isekai'd. So she died, I think. I forgot. It's not a spoiler. It happens in episode 1, I believe. So this girl dies. It reincarnated into this fantasy world, but she's actually supposed to be the villain of that world. But turns out she's such an airhead that doesn't happen. Anyway, it's a harem, so almost all the guys and girls like her. So there. And my favorite character is not there. My favorite character so far is in the second season, which is this guy, the blue-haired guy, and his name is Sora. So Sora. I like his backstory. So yun lang, I just wanted to share. If you're trying to look for a funny anime, I suggest that. Yeah. Okay. So again, My Next Life as a villainess. So that's why that's a title, because she's supposed to be a villain. Alright, that's it. Just wanted to share. Again, the name is Sora. The blue-haired guy with the glasses. Okay. So since you don't have any more questions, you may go. Please review for your exam on Saturday. Goodbye, class.